Yeah, it looks like it's going.
Okay, we're live.
Right.
All right, Andrew, you're in charge, right?
All right. Yep. So let's just get started then. So welcome back to part 2 of my discussion on QCD spectroscopy. Let me share my screen. All right. So hopefully everyone can see my slides. Let's do some little Zoom cleanup around here. All right. So last time we, let's see, there's already a question. Okay, I'll let Raul deal with that one. So there is, so last time we discussed the basics of going into scattering theory, which is a way, let me, since I didn't create a summary slide, let's just start from here. So the whole idea behind a lot of techniques I'm showing is, since we can't calculate a lot of low energy, strongly interacting physics from QCD directly, using kind of standard perturbation theory techniques, a lot of what we know is inferred by doing analysis on experimental data. So here's an example we were kind of taking through as we go along developing the framework. We have neutron proton scattering, and you have these blue dots, which are actual data points, and then some curve, which is a fit to this data from some theoretical scattering amplitude, which is the central object that we use to study all the dynamics of some interaction. So we discussed how to kinematically describe such reactions, and now we're moving into descriptions of the scattering amplitude. So I just want to keep in mind, the end goal is to develop enough of a framework in order for you guys, in which I think when Andre talks about some data analysis techniques, this will be another example that's brought up, where you will use a lot of the framework that I'm showing here, distill it down to its essentials needed to describe this type of process, and you will analyze this data and reconstruct curves like this red curve here. So let me now jump to where we need to go to. So last time we did all the kinematic descriptions. We had some discussion on the importance of complex numbers at the very end, in which, again, in the PDF of the slides, which are on the Dropbox, you have all these kind of little details of complex numbers. If you haven't seen them before, this is a nice quick summary of kind of essential operations. If you have seen them before, then you know these should be familiar to you. So we need the technology from complex numbers because quantum mechanics requires complex numbers in order to properly describe the physics of some situation. And we discussed the importance of these probability amplitudes, which are what quantum mechanics can give us. So in quantum mechanics, reaction dynamics, specifically for some scattering reaction process, are encoded in scattering probability amplitudes. So let's denote kind of schematic how this setup works. You have some initial state. So this psi is just some general placeholder for some initial state. This could be the neutron and proton of our scattering system. There's some probability amplitude, which here we denote as S for scattering probability amplitude, which is an energy dependent amplitude. So it depends on our kinematic variables that we already set in, got all the setup done. And we saw that we only really needed 2 independent variables to describe this neutron proton elastic scattering process. The total center of momentum frame energy, the star, if you remember, means that we're evaluating it where the proton and neutron are in a frame going back to back. And this angle theta is the scattering angle between the initial neutron and the final neutron. So the probability amplitude for this initial neutron proton state describes the transition from this initial state to this final state, which in the case that we're studying here is another neutron proton system. But in general, this could be whatever type of particle reactions you want. You could have, say, a neutron proton going to a neutron proton, plus you produce one of these pions, one of these light strongly interacting particles if the energies are high enough. And then you'll have a probability amplitude that then has all that dynamics encoded inside of it. So this here has all the dynamics of this reaction. And it depends on the kinematic variables. And in this case here, since we're dealing with this 2-to-2 type process, it depends on the energy and the angle. And the probability for the initial state to evolve to this final state is simply the modulus of this probability amplitude squared, which that is what I'm showing here. So this is in the same line of typical quantum mechanics teaching. Have some probability amplitude, take the modulus, which is the complex conjugate times itself, and that is your probability distribution for going from some initial state to some final state. So before I was saying when we were talking about the reaction kinematics that we're not going to focus so much on the angular dependence. And so let me discuss real briefly how we're going to justify that. So for this proton-neutron system, there is a rotational symmetry, much like all these other symmetries that encode the physics. So Vincent was talking about a lot of these different symmetries, isospin, and there's energy and momentum coming from translational symmetry. So all these different symmetries lead to conservation laws. So one of the things that we can do is use this kind of rotational physics in order to simplify our analysis. So a neutron and proton can orbit each other with some orbital angular momentum, which I'll call L here. And because it's quantum mechanics, orbital angular momentum is quantized. So you have L is equal to 0, 1, 2. And again, this is all in units of h bar, where h bar is equal to 1. So you have this proton and neutron orbiting each other. And just like in the hydrogen atom, you can break up a system that has some rotational properties into a series of orbitals, which describe the angular content in terms of their angular momentum quantum numbers. So in this case here, schematically, I'll write this as that this S probability amplitude that is a function of E star and theta star, we can write it as some series of different orbital contributions. The lowest one is a spherically symmetric orbital distribution with a weight function called S0. And this 0 here is corresponding to 0 angular momentum. So here I put a more concrete formula down if you're interested. You have some series in angular momentum with some weight function that depends on the angular momentum, and then some rotational function, which is described by this pretty picture of this orbital here. So this orbital is the S wave orbital, and this is the lowest angular momentum state you can have. The next highest up is the P wave orbital, which hopefully sounds familiar from chemistry when you talk about these different orbitals. It's the same idea. You have some angular momentum in the system, you can break it up into these orbitals, and you can continue having a bunch of different angular momentum that are more complicated. Each of these angular momentum configurations, which is associated with the angular distribution of the two particles, have a weight function, which are generally, just for your information, called partial wave amplitudes. But really, we can just think of this thing now as a reduced amplitude that has 0 angular momentum and now has no longer any rotational dependence. This one has 1 unit of angular momentum and no longer any rotational dependence, 2 units, blah, blah, blah. And these are the SP and D waves, and these are the weight functions associated with the rotational dependence. For low energy scattering physics, the isotropic interaction dominates. So that is the lowest angular momentum distribution is the dominant one for very low energy physics, which that is the case that we're studying here with the neutron proton scattering. So this is my justification for why we're going to ignore the angular dependence, because at low energies, this amplitude will dominate above the rest. And of course, you can add these back in, and when in actual an analysis of scattering data, we do this. We include all these, as many angular momentum contributions as we need to describe the system, and we determine what their weight functions are. In this case here, we're going to assume the isotropic type of distribution, so there's no angular dependence. And instead of writing this S0 everywhere, I'm just going to replace it by S. So S here, even though you can have a general scattering amplitude, scattering probability amplitude that depends on all these different angular distributions, we're going to just keep it simple and just deal with the lowest energy one. There's some other physics that's encoded inside this probability amplitude. And in general, this S describes the evolution of some initial state to some final state. I see there's a Q&A. Okay, there's still some questions about some admin stuff. So there is a case when you can have the initial state evolving to the final state where the particles do not interact. So you can have a proton and neutron just kind of passing by each other and not talking to each other at all. That's not very interesting when it comes to scattering physics. We want all the scattering physics. Oh, there go my dogs. So because we want all the scattering physics, I'm gonna mute real quick while they do this, sorry. I apologize. My dogs like to bark at inopportune times. So we want to remove the piece of the probability amplitude where the particles do not interact, since it's not very interesting. So we will define this S then as 1, which 1 is the identity operator here, meaning that the particles don't interact, plus some prefactor 2I. I won't explain where this really comes from. It's just some convention that us particle physicists use. You can choose different ones if you want. It doesn't, at the end of the day, it's just some normalization that pops out at the end of the day. You have some kinematic factor. And if you remember, I went through this justification of having the available phase space that these two particles can take up. Well, this is where it starts creeping in. We're going to have this kinematic factor now become explicit, where this phase space factor here describes the kinematic distribution of the two particle system. And we have M here, which M we call the scattering amplitude. I was trying to be a little careful and call S the scattering probability amplitude. It's got some other names, but I don't want to just bombard with a bunch of different definitions. But when we talk about scattering amplitude, really what we're going to focus on is just this M amplitude, which encodes all the dynamics. So we've removed all of the trivial cases where the particles don't interact. All the dynamics are encoded in M, and we have some normalizations, including the kinematic distributions of how the systems can take up their energy space. The scattering amplitude M is the same object that's related to the cross section. So in the cross sections, you remove the cases where the particles don't interact, because again, that's not the interesting case, and that's not what you're measuring when you measure such random cross sections. So this is where this M appears in actual reaction data. Note, sometimes people call M different letters. Sometimes they call it T, A, R, blah, blah, blah. Just know if you see this in the literature, you may see it by different names, but here we'll just stick with the scattering amplitude M. Okay. So now we have our definition of what the scattering amplitude is. Let's see what type of properties this scattering amplitude, and in fact, all scattering amplitudes must have for any type of reaction. So one thing that we want to impose is that probability is conserved. We're dealing with quantum mechanics, so we deal with these probability distributions. And since we're dealing with probabilities, we want probability to be conserved. It's a fundamental tenet of physics. So if you have some initial state go into some final state and you sum over all the possible final states, well, that total probability has to be 1. For elastic scattering, since this probability distribution is this modulus S squared, you find for elastic scattering, you only have one possible final state. So we have neutron proton going to neutron proton. There's nothing else. That means that this modulus squared, since there's only one final state, must be equal to 1. So this is a pretty tight constraint on this scattering probability amplitude. What does this mean for the scattering amplitude itself when we take out the identity piece? Well, one can show, and in fact, this is one of your exercises, is that when you have this condition from probability conservation, and you use the definition of scattering amplitude, you can show that the imaginary part of m is equal to this kinematic phase space factor rho times the modulus of m squared. So remember, we're dealing with these quantum mechanical probability amplitudes. They're generally complex numbers. At some fixed energy, it's a complex number. So it has both the real and imaginary part. And this condition here imposes that the imaginary part is constrained to be this kinematic phase space factor times the modulus of the amplitude squared. Like I said, this is one of your homework, one of the suggested exercises, it's just to derive from this condition, So this is the unitarity condition on the scattering amplitude. At a fixed energy, the amplitude needs two real numbers, as I said, the real part and the imaginary part. And this unitarity condition relates the real part and the imaginary part. Some technical note here, which I'm just going to say, if you start thinking you want to explore the scattering physics and do a bunch of cool things, is that for elastics, this statement is true only for elastic scattering. This means it's true for when the energies are above the threshold energy for the two particles, in this case, the proton and neutron, but it's only valid up to the first inelastic threshold. So if we imagine we create a pion in neutron-proton collisions, so you have a neutron-proton and you have enough energy to where you can create a pion. In particle physics, which combines special relativity and quantum mechanics, you can pop particles out if given enough energy, pop particles out of the vacuum given enough energy. And this condition only holds up until where you start producing more particles. So I call this mass scale mu, which you can think of as the mass of the muon. Not mass mu, mass of the pion. And this condition holds only in this blue region here. So here I write this little cartoon of the energy plane. The real energy axis is going to the right here. The blue line is the elastic scattering region, which is the case we're actually studying here. And this condition holds here. If you want to increase energies, you need to add additional terms because now you're producing more particles. So that's the general game we need to play. But because we're dealing with low energy physics, kind of physics around this region here, we can safely ignore any of these other higher threshold contributions. We can, there's a question here. So how do we define the norm of the matrix M? So can I go back? So here, this modulus of S squared, this norm squared, is just equal to the complex conjugate times itself. When we're dealing with the scattering amplitude, it's the same definition. So this is just the complex conjugate times the amplitude. The complex conjugate of the amplitude times the amplitude is the meaning of this mod squared. I hope that I think that answers the question that you're trying to ask here. Yeah, okay, good. Yeah, so this is, again, a complex number. You take m star m times rho, and that must equal the imaginary part of m. Yeah. So as we were saying, in general, you would need two real numbers, the real part and the imaginary part. However, the imaginary part is constrained. If we do a little mathematical trickery, which again is an exercise, you can rewrite this condition as a condition for the inverse m. So inverse m here, I mean 1 over the scattering amplitude. And you can maybe see it real quickly by dividing by the modulus squared on both sides, and then using properties of complex conjugation and the imaginary part in order to reduce this as the inverse m. But what we see here is that the reciprocal or the inverse of the scattering amplitude, actually I'll use those interchangeably, I won't be too stringent on mathematical language. The imaginary part of this inverse scattering amplitude is equal to minus rho. So the imaginary part of this inverse scattering amplitude is fixed completely by kinematics. So here we were saying that the scattering amplitude encodes all the dynamics of the system. This unitarity condition essentially fixes part of the amplitude to be completely dominated, to be completely described by kinematic quantities of two particles interacting. So because of this, we can write a general form for the scattering amplitude just by recognizing that we only need one real number to completely satisfy this equation and satisfy I'm sorry, to satisfy this equation and specify any scattering amplitude. So this general parameterization, which is called the K matrix representation, in terms of the inverse scattering amplitude, and you can do some quick algebra to write this in terms of M instead of M inverse. I'll leave that to you. M inverse is equal to K inverse, which is a real function which must encode all the dynamics because the imaginary part is completely fixed by kinematics. So we're boiling down this general complicated object to simpler and simpler things that we can analyze and fit to scattering data. So now instead of having to fit two complex numbers, I'm sorry, two real numbers for this one complex number at each energy, we can separate all that out, and we only need to specify only one real number at a given energy. And if we can get what this K matrix is, then we know everything about the scattering dynamics. So in perturbation theory, if you're doing something like quantum electrodynamics, and you calculate the scattering amplitude order by order in the coupling constant of the, in terms of the electromagnetic coupling constant, really what you can think about doing is kind of writing this in this way, and you're calculating the K matrix order by order in this interaction. So all the interactions are encoded in there, and you should be able to show for any quantum electrodynamic amplitude that for this two-body amplitude that you can separate out this kinematic piece, and all the rest of the dynamics are encoded in some real function. Same is true in the strong interactions of QCD, and this is what we're going to use to try to analyze data. So some exercise show that this imaginary part of the inverse amplitude is equal to minus rho. From here, you should be able to quickly deduce this, just because the imaginary part is this. So here's a factor of I, and then this must be a real function. All right. So we want to know this whole thing. We can split this thing up into a piece that we know. This is a known function. We know what Q star is at a given energy, and that's what feeds into this phase space factor here. And we want to determine this function. That's our kind of goal set now that we have in analyzing this neutron proton scattering data. It is useful to write another representation of the scattering amplitude, which is closely related to what you may see in non-relativistic quantum scattering. So I want to take a little bit of time to describe that, and then there's some additional physics that comes out from there, which I'll simply state. I'll leave it to you to kind of verify by going through non-relativistic quantum scattering. If you've taken it, or if you haven't taken it, you'll see it. So with unitarity as a starting point, we can derive a phase shift representation of the scattering amplitude, where we use the polar representation of the scattering amplitude. So remember, with complex numbers, there's this Cartesian representation, x plus iy. There's also this polar representation, some radial part and some phase part. So here, M in general needs two real numbers, this phase delta and this radial, which is just the magnitude of the scattering amplitude. Unitarity fixes the imaginary part to be related to the real and imaginary parts. So if you substitute this thing into here, one can show, and again, this is an exercise, that if you impose unitarity on this general scattering amplitude, you'll find that M is equal to 1 over rho, the same kinematic factor that comes about over and over again, times some exponential of delta times sine of delta. So here, the only thing not known is one real number, and that is the phase shift for a given energy. And this phase shift also encodes all the dynamics of the interaction. So we have this K matrix representation, which all the dynamics is encoded in the K matrix, or you have this phase shift representation, all the dynamics is encoded in this delta phase shift. So obviously they must be related, and an exercise is to one, derive this relation, and two, show that K matrix, just by simple trigonometric and exponential identities, show that the inverse K matrix is equal to rho times cotangent delta. So here, rho is a real function, it's a function of kinematics. Delta we said is a real function. So this rho cotangent delta is a real function, which aligns with our ideas that the K matrix is a real function. So we have these two different descriptions. Often you can use in some analysis either the K matrix or the phase shift to describe reactions. Often you use both. it's easier to parameterize one, say in terms of some fit parameters, and then the other one. And oftentimes you want to look at both of them to get some physical meaning out. So here, now we're going to start, we have this general K matrix function, which is related to the phase shift via this relationship here. Rho cotangent delta is proportional to Q star cotangent delta, where, because rho is Q star over 8 pi E star. So there's just some prefactor out here. How do we make sense of this function to use in some scattering analysis? Well, it's a real function. So you can do at low energies a Taylor expansion of this function in terms of the energy, or equivalently the relative momentum, and the parameters, the expansion coefficients will be real functions, and then we want to assign physical meaning. So here is an example. It's called the effective range expansion, where I expand this thing out to two terms in Q star squared. The first leading order term is just a constant. The second order term depends on Q star squared. And then there's higher order terms that you could include if you so desire. But let's focus on these two. I write these in a slightly weird way, but the reason why I write them down is, again, to compare to non-relativistic potential scattering theory, where this A here is called the scattering length. So the scattering length has units of length, but again, in these natural units, length is equal to inverse energy. And this scattering length here essentially describes the strength of interactions. So if you have a potential well and it's very, very deep or very, very shallow, this A parameter here is giving you a characteristic scale of the strength of that potential, the strength of this interaction. And it's written in this funny way, just from historical ways and giving some physical meaning to this A as the amplitude gets near the scattering threshold, and we'll go through that in a second. The second term here with this R parameter is called the range. It's called the effective range, and it qualitatively describes the range of interaction. So how big this potential well is. There's some factors of a half here and minus signs, and they're just kind of conventions that we choose. But ultimately here, we are now taking this real function and writing it in terms of physical variables, the scattering length, which is the strength of interaction, and the effective range, which is how far this interaction goes. And we don't know what these real numbers are. These are real numbers. They're independent of energy. All the energy dependence is encoded in the momentum. If we could determine what R and A are, if we can determine the scattering length and the effective range from some fit to data, then we can get some information about this interaction. As an example for what I was saying before with the scattering length, one can show that as you get near threshold, so the scattering amplitude when you get to the threshold energy, which is just twice the mass of the particles, that the amplitude is fixed by some prefactor times the mass times the scattering length. So here you see for a very small scattering length, the amplitude is very small. So it's not that strongly interacting. If the A is really, really big, then the threshold value of the scattering amplitude is huge. And that's telling you you have a large amount of interaction. So as an exercise, show that at threshold, this amplitude is constant and fixed by the scattering length. All right, so let's go back to our neutron proton scattering data. We have this effective range and the scattering length, which we want to learn about the neutron proton scattering interaction. We have some data. We know how the scattering amplitude relates to the cross section. We now know how to cast our amplitude in terms of this phase shift K matrix representations, which we then use to write in terms of physical parameters like the scattering length and the effective range, plus with any other parameters you want to, that you can so fit in there to describe the interaction. So the goal is now becoming, we have the blue dots, we have a mathematical form for M, we want to fit this data to find what A and R are. And then once we have that, we can start learning about the interaction. So we'll go through that and show an example of what you get out. But let's go to the next step first of once you do that, what you could do next, and that is the spectroscopy part. So looking at what is the spectral content of this interaction? Does it form bound states? And then what are the properties of these bound states? So remember that the scattering amplitude encodes all the dynamics. So we should be able to ascertain the spectrum by studying the amplitude. And at the beginning, we kind of illustrated that scattering is related to bound states, as these bound states are enhancements in the amplitudes. They are these pole singularities, which are such that the amplitude gets enhanced near when this denominator goes to zero. And in general, the pole singularity, which is a very fancy term for just this denominator going to zero, when the energy gets very close to the mass, then this denominator gets small and the amplitude gets large. You have two parameters here governing the pole, the hadron mass and the hadron decay width, which is related to the hadron lifetime just by taking the reciprocal. Now, if the hadron is stable, so here again, here's a cartoon of this energy plane. If the hadron is stable, then its lifetime is infinity. So its decay width is zero, which means then you just have a real pole when E star equals M, this denominator goes to zero and the amplitude diverges to infinity. So stable bound states, which is where the lifetime is infinitely long, occur as a pole, which is just some 1 over X type singularity, where at some place below the scattering threshold. Unstable states have a finite lifetime and thus have a finite decay width. And these things are poles not on the real energy axis. So they diverge only when the energy is complex. So when it has a complex part to cancel out the decay width. And so it's often the complex plane here. I don't really want to talk too much about resonances at this time. We don't have enough time to really go into these details, but I want you to be aware of it. These unstable states, these resonances, we can describe in the same way. However, they're a bit more complicated. In the case we'll be focusing on is the deuteron. It happens to be a stable bound state, so it's an infinite lifetime. So it's a little bit simpler, but I want you to be aware of this general situation. So how do we determine this, the spectrum of the scattering amplitude? So where the mass and decay width of any sort of composite state being formed are? Well, we look for zeros of this denominator. Since when this denominator goes to zero, that's where we can pick out the real part related to M and the imaginary part related to gamma, which is related to tau. So this is the condition when E star at a specific value, which I label as B here for bound state. When that occurs, when this is zero, then we can identify these parameters, these parameters here. So as an example, let's go through a different version of the phase shift representation, which you can again show just by relating to the K matrix. As M is some numerator term divided by Q star cotangent delta minus IQ star. So when M inverse goes to zero, you're going to have that this denominator is equal to zero. Therefore, Q star cotangent delta is equal to IQ star. So here's just an example of kind of how you apply this logic, algebraically at least. Let's assume a leading order effective range expansion. So Q star cotangent delta is minus 1 over A. So imagine we determined A from some fit. It's governing the interactions. And let's assume we're at low energy such that we can ignore all the higher order terms. Well, in this case here, if you substitute this thing back into here and look at what value Q star is equal to I over A. And we define this real part that is multiplying this I factor here as the binding momentum. So it's an imaginary momentum that describes kind of how much binding this system is feeling. The reason why we write it in terms of Q star is because then we can plug it into the formula for the center of momentum energy in terms of Q star. And when you substitute I times I, you get a minus sign. This is where this minus sign comes from. And you have that the energy at this bound state, sorry, I forgot the B label here because I'm going to the bound state location, is equal to twice times the square root of m squared minus kappa squared. So this is the location of this bound state pole. And if we relate to the general definition we gave, we find that the mass of the particle is equal to, if there is no imaginary part, which here we see that E star is equal to some real number here. Imagine, in general, kappa squared for these type of systems will be lower than m squared. So this is a real number. There's no imaginary number. Therefore, we can identify immediately in this case that gamma is equal to 0. So we have a stable bound state. And the mass of the particle is twice times the square root of m squared minus 1 over a squared. So the mass of the bound state, if a were, I'll go through that later, right? So this is the values of the mass and decay width of the particle. It's a stable bound state. For this positive a, and for a, for this positive a value, we find that m is less than 2m here, all right? So 2m is the threshold point. This mass is being shifted downward, so we can define the binding energy, which is how much energy is needed to bind the system or to break the system apart if it exists, as the threshold energy minus the bound state mass. So if the bound state is, so as a function of energy, the bound state is here, the threshold energy is this point here, and this difference is just the binding energy. All right, so this is a bunch of kind of formulae that I'm just showing you without any really physical example here. Let's go and apply this, apply these ideas to the neutron proton scattering system and see what we can get. So we're going to start describing now the neutron proton scattering process, and we have all the scattering theory tool set in our tool chest here, which is the kinematics, how to describe scattering amplitudes, the relation between scattering amplitudes and cross sections, and then how to get the spectral content afterwards. There is one thing that's missing though, and that's spin effects. So here, again, the idea is we have our kinematic description of this reaction. We can we have the data to convert to scattering amplitudes. We can parameterize the scattering amplitudes into some unknown parameters, which we can get information about the interaction. Once we have these parameters, we can then search for when the denominator goes to 0, and this will correspond to any bound state. In this case, we're looking at the deuteron, which is a bound state of neutron proton scattering, and we can get information from there. But this is a neutron proton system. Everything I'm describing so far doesn't take into account the fact that neutrons and protons are fermions. They're spin 1/2 objects, which Vincent talked about last week. So they have some other degrees of freedom, which are not kinematic. So in order to properly describe the data, we do need to take this into account. So I'm going to take a few moments to just build this in intuitively, I hope at least. So the nucleons have some intrinsic spin. They're spin 1/2 fermions. These strong interactions do depend on the spin degrees of freedom, and they don't need to, but in general, just from, we know they do. And if you didn't know that, you would build it in and find that the spin doesn't really contribute to any sort of interaction. But here we know they do, so we know we need to take it into account. So we're going to still assume this low energy regime. So there's still no angular dependence. So as the proton and neutron are orbiting each other, they're in the lowest angular momentum state, but the spins can still talk to each other. So a nucleon spin, it has two projections. It has two components. It can either be spin plus 1/2 or spin minus 1/2. So here's just some z direction here. The spin is some spin 1/2 vector, you can think about it, and it can either be pointing up or pointing down. If you have a neutron proton system, well, then you have different possibilities for how these spins talk to each other. The total spin projection of the neutron and proton will be the sum of each of the individual spin projections. And we see here the top is the neutron and the bottom is the proton. So here, let's look at an example. This first example here, the neutron is spin up, the proton is spin up, Therefore, the total spin projection, Sn plus Sp, is +1. In this case here, you have -1, -1/2, -1/2. So if you add them up, you have a total spin projection of -1 for the two nucleon system. And in this case here, you have the neutron spin up, the proton spin down. So the total spin projection is 0. However, the spin projection can be 0 in a different way. So we can think about this case here as they're symmetrically 0. And in this case here, you can also have it to where they're anti-symmetrically 0, meaning that they're out of phase by each other. So this is a pictorial representation of this out of phase. The mathematics behind this is the same mathematics that Vincent showed with these Young tableaus and counting the spin degrees of freedom. So ultimately what we find is that we have a triplet of symmetric states, and we have a singlet of an anti-symmetric state. So we will label the singlet by a total spin 0, and we will label the triplet by a total spin 1. All right, so this is our spin 1 state, our spin triplet state, and this is our spin singlet state, our spin 0 state. So these are how the spins couple. And if this is too much for you, I apologize. We can just take this kind of result and fix our cross section. So our cross section we describe for one kind of not dealing with these spin effects. When you include the spin effects, the total cross section is the weighted sum of the spin triplet configuration, where the spins form symmetric pairs, or the anti-symmetric combination where they're anti-aligned and anti-symmetrically formed. So if we count, let me go back here. So if we count the different spin configurations, there's 4 here, 3 for the triplet, 1 for the singlet. So the total cross section will be the weighted sum of the singlet cross section. I'll use S here to denote spin singlet, and T here to denote the spin triplet. There's a total of 4 possible states, 1 in the singlet and 3 for the triplet. So even though we're dealing with no orbital angular momentum, we are dealing with an intrinsic angular momentum coming from the intrinsic spin of the particles. So the total angular momentum of the system is completely governed by the spin angular momentum. Since L is equal to 0, there's no interactions between the spin and the orbital couplings, and the total angular momentum, which I'll call J here, is just given by S, which is the either spin 1 or spin 0. So now we have everything that we need now to mathematically describe this reaction and fit the data. So the total cross section is this weighted sum of spin singlet and spin triplet. Each of these individual cross sections, I use X here to denote a placeholder for either S or T, because it's the same type of form for each one. The exact relation between the cross section and the scattering amplitude is given by the modulus of m squared, and then there's some prefactor here. M here for each the spin singlet and triplet is given by this expression here, which again was just found from the K matrix phase shift relation. And what you can do then is write your phase shift in terms of the effective range and the effective range parameters. And when you do that, I did all the math for you, so you can just go ahead and use this final formula if you so desire. You can also prove this to yourself if you want. The final formula for each of these spin cross sections is 4 pi, which this 4 pi is reflective on the fact that we have some isotropic interaction, so there's no angular dependence, divided by this denominator here, which includes the scattering length, and it depends on if it's either triplet or singlet. So you can have so in general, they could be different. If you find that they're the same, well, then there is no spin effect. In general, there is a spin effect. So A of S will be different than A of T. We have the effective range here. I'm ignoring all other higher order terms. And it's a function of Q star squared, which is a function of the center of momentum frame energy. The scattering data I give here is in terms of the kinetic energy of the neutron. So it's not of the kinetic energy of the neutron in the lab frame, not in the center of momentum frame. I briefly showed the relation of describing the kinematics in that frame, and here I just give the relation of q star squared equals 1/2 mTn. So here, really what you have here is this individual cross-section is a function of these two parameters, which is also a function of the mass of the proton and neutron, and through q star, a function of the kinetic energy of the neutron. So what you could do here is take this form, plug into here. You have 4 parameters you need to fit: a scattering length and effective range for each the spin singlet and triplet. And this resulting curve here I show here is a result of fit to that data. And again, Andre Walker-Loud will be going through examples of doing data analysis. And I think this will be one of the examples that he discusses. So you may get a chance to play with this data a bit more freely. Here, I'm just kind of giving the background information necessary to do this analysis. So here you can do a simple chi-squared analysis, and I will not talk about chi-squared fitting here. I'll leave that for Andre. But essentially, you compare the experimental results and the errors of the experimental data to the theoretical model. I put some conversions here to relate Fermis, MEVs, and barns, all these different units that Vincent was talking about. And I'll show you the result from my simple fit. So I get a chi-squared per degree of freedom. So I have 486 points of these data sets. And I'll put these data sets on the Dropbox as well, so you can actually plot these things and take a look. I formatted them so you can kind of, so they're more easy to read. And Andre will talk more about them later too as well. So my chi-squared per degree of freedom is about 0.98. For good fits, you want this chi-squared per degree of freedom to be about 1. So this is not looking too shabby. And I get these parameters here. I'm ignoring all the errors and stuff that come along with this. Let's just focus on nominal numbers right now. I get that the triplet effective range and scattering length is to be this here, and the singlet to be this. So great, these are some numbers. We now need to get some physics out of this information. And the physics we're gonna get out is the spectrum of these, of the spectrum of this interaction. Just a note, you can compare this to a paper by Hackenberg, some analysis that is a really good analysis using a large data set. And these are his numbers, and I can also link the paper in the Dropbox as well if you're interested. And you see here that the scattering lengths, this A of S and A of T, I actually don't do a pretty bad job. I get pretty close, and with more decimal places, if I kept the errors here, I think I do agree pretty well with this. The A of S and A of T are really dominated by the low energy physics. I see there's a question here. What does negative scattering length correspond to? I'll get to that in a moment. The effective ranges are not as good, and there's a reason for that, and it's because the way I've presented how to do this, there can be a lot of correlations between these parameters, and I don't want to talk too much about correlations, but if you do a better analysis, such as what Hackenberg does, where you put in some extra physical information here to better represent the system, you can get these numbers out a lot better to what's accepted for this low energy scattering process. But still, even with my simple fits, we do a pretty good job of getting qualitatively the description of the interaction. So the signs of the scattering lengths reflect whether or not the system is attractive or repulsive, but that's not strictly true. So what you end up finding is that for a very large positive scattering length, you are essentially forming a bound state. And that is what is happening in this triplet state here, is that we will find that there's a bound state formed in the spin triplet configuration, which is the deuteron. This negative scattering length, you still have an interaction, but it's not as strong. And it is, it's forming, it's not strong enough to form a bound state. There are some subtleties with kind of what this means, and we can be a bit more precise However, I'm not going to spend that time here because I'm already running pretty long, but I can recommend some books, some basic quantum mechanics books, because it's not as simple as a positive or negative sign mean repulsive or attractive interactions. The size of the A's also matter. And it's not just the size of the A's, it's the size of the A's relative to the mass scale. So the mass scale and the scattering length here is very large for here, whereas here it's not as large and it doesn't form binding. So I'm being wishy-washy with that answer. I apologize. We can try to talk more later on Zoom, Slack. I can try to give some references. All right. So an exercise, given my fit results, so given these parameters here, these conversions and the equations on the previous page, plot the cross section. So plot this thing here using this formula as a function of the kinetic energy using my numbers here. And then you can repeat it for these numbers and you can see how much of a difference it may make. You may see that it doesn't make much difference at all. And again, that's indicating some large correlations inside that these parameters, are sharing. So now in the last kind of few minutes, I want to look at the bound state spectrum of the proton-neutron system. And this is the deuteron. So we'll focus on the spin triplet, as I was saying here. The triplet state, and this just comes from hindsight. If you were to do this analysis, you would do it on both and see what you get it from it. I'll leave you to that to do some exploration. Since this is, science, you should do some explorations by yourselves if you're interested. The spin triplet configuration does form a bound state. So we're going to focus on the spin triplet results here. So we're going to search for poles of this scattering amplitude. So that's when M inverse is equal to 0. And because of this, we have this equation, which is quadratic in Q star squared, but it's a complex quadratic because the coefficient that generally has an imaginary number here. So you can do this algebraically if you wish. You can do it numerically. Here, I'm just giving the final result. What you find here with my simple fit, so this is what my numbers, is that you get a deuteron with a mass of 1878 MeV. It's got it's a stable bound state, so it lives forever. And it's got a binding energy of about 2.1 MeV. So these are the energy units that we measure things in. The threshold, I thought I put it there. The threshold for a neutron proton system is then 2.1 MeV above this number. If you use Hackenberg's numbers, so this is more of the kind of the best analyses, you find that the deuteron mass is 1875.6 MeV and the binding energy is 2.2 MeV. So here with this simple fit, and this is a fit that you guys can do, and I think will do as an exercise in the coming weeks. Once you do to fit the data to get these numbers here, you can then use the scattering theory knowledge that I've given to find what the bound state spectrum is, and you find results that are not too far off the accepted results that we have in the literature. And here I'm again ignoring a bunch of decimal places and the errors associated with these things. So even kind of these simple approaches to this, you do get some physics inside out. So what do we find? We find that, and again, given my fit results and Hackenberg's, solve this equation for these parameters here. It's a simple quadratic. If you have familiarity with it, you can do it numerically or you can do it by pen and paper. So what we have found is that we have this bound state spectrum from the neutron proton. We've determined that we have a deuteron, which is a shallow bound state of the triplet S-wave neutron proton scattering. So I say shallow bound state because it's got a very small binding energy, and here I'm showing the kind of best available. It's got a small binding energy, and we know it's got infinite lifetime. From the quantum numbers of the scattering, so we said that this is a spin triplet system, so its S is 1, its intrinsic angular momentum is 1. We also know that the orbital angular momentum is 0, so this is S-wave triplet scattering, L is equal to 0, S is equal to 1, that the total angular momentum is simply given by the spin interactions. So we know the total angular momentum J is equal to 1. So this is a vector particle. The other examples of vector particles is like the photon, the rho meson, if you're familiar with it. They are vector particles, which means they have 3 spin degrees of freedom. It also has parity, which I really didn't talk about at all, but parity essentially is just indicating what orbital angular momentum the system has. In this case here, parity plus means it's an even state. 0 angular momenta are even states. So we can go through our spectral properties checklist and start indicating what we've learned about the deuteron from basic neutron-proton interactions. This bound state forms, we know its lifetime and its mass. We know its spin, its parity, so how it changes under reflections. We know its charge, that was one of the things we saw earlier. And there's some other properties we can get from it by doing further analyses. I don't really have any more time to discuss a lot of other things in detail, but this is, if I can just summarize here, what I've gone through is what we do in QCD spectroscopy. So from the experimental side, we take some experimental data, fit it to some scattering models that have some physical parameters that we can try to fit and understand. From that, we look at the spectral content of the theory and we're able to discover and quantify, classify new particles, which is a thing that we're all interested in doing nowadays. On the theoretical side, from lattice QCD, the same scattering analysis applies, except there, instead of dealing with experimental data, you are calculating different different types of observables that Raul mentioned in his first set of discussions, and you can relate those to scattering parameters by some sophisticated formalisms that I and Raul and Andre and a few others work on. So I won't say more about that because that can be a whole nother 2 weeks by itself. But I hope this gave you a good flavor of what QCD spectroscopy is about. I'll put the slides up online. I'll drop in the data sets that you can look at. I think Andre will also give you the data sets. And I hope I gave you at least enough of the mathematical framework to describe a scattering process, showed you this example, and then hopefully you get to play with that example in a week or two. So thank you. Are there any questions? Or did I completely lose people? I see there's a hand raised. Aditya, you want to ask a question?
Hello, can you hear me?
Yeah, I can hear you.
Yeah, I'm not sure if this question has been already asked or this has been discussed, but when we're discussing about objects like the S matrix and M matrices, they're essentially matrices, right? So in all the algebra that we do, and while treating them as complex numbers, how do we ensure that that also checks out simultaneously? Like when expressing it, like when expressing M in terms of E to the I delta, how do you interpret?
Yeah. So everything. So you are right. In general, these quantities here, which I'll go here. These quantities here, S and M, are matrices. And they're matrices in all the available quantum numbers of the system. So this would be like angular momenta. They're matrices in the number of scattering channels involved. They're complicated matrices. So in general, you would have to be careful by doing matrix algebra. The philosophy is the same. So it's the same philosophy that I presented here. It's just you get some technical details of treating these things as matrices. So here, instead of having this simple relation here, it would be a matrix product with the Hermitian conjugate instead of just the complex conjugation. Because here I'm considering these things as a single scattering channel, so it's a single complex number. But in general, it's just a matrix of complex numbers you then need to constrain, and then you just use your techniques from linear algebra. But in general, the principle is very much the same. It's the same philosophy. You just now need to deal with matrices and deal with them properly.
Right. Yeah. Sorry, I was just confused. Just wanted to confirm that.
Yep. me stop sharing so I can. Are there any other questions or comments?
Yeah, can I ask it directly without raising my hand?
Can you say that again? I couldn't
Yeah,
hear
yeah.
you.
I wanted to ask something. I did not raise my hand.
Oh, yeah,
Okay,
sure.
so I wanted to ask, am I audible clearly?
You're a little low, but I think I can make you out.
Okay, okay. So I wanted to ask if let's say we know that for bound states we have we can safely assume that that time is basically it will be the time factor will be 0 in the equation that you show. Okay, so let's say now we need to study some unstable particles. So is it a prerequisite that we know the mean lifetime or lifetime of the particle beforehand?
No. So that's a good question. No. What you'll find, so in the, let me go to an example here. So here I was showing that when you have M inverse is equal to 0, that you have something like this. In general, there's other parameterizations that could exist. There's other situations that may arise, but for this specific example, we found a real bound state. But in general, what you'll find is that when you have M inverse is equal to 0, you'll find that you'll get two pieces, one real part equal to 0 and one imaginary part equal to 0. And so you don't need to know this a priori. You can determine it from this type of equation. And this is an example of such case would be like the Bright-Wigner amplitude, which I didn't discuss here. Maybe I can do this really quick if I am able to. So these are some old slides, but I know I have plot. All right. So in this example, so this is a plot of a scattering amplitude for a Bright-Wigner type process, which is where you have an unstable particle being formed. And in here, you see a bump on the spectrum, just like before. Generally, when you fit this data to some parameterization, you'll find that your denominator will have a non-zero gamma. And that non-zero gamma then is the decay width. So it's not something you need to know beforehand. It's something that the fit to the parameters will tell you. Answer your question.
Yeah, thank you.
You're welcome. All right. Well, if there's no other questions, then maybe it's time to sign off then. I would say. So yeah. So I don't know the times next week for them, but I know I'm pretty sure Andre is talking next week, and he'll be. It's still going to be Tuesdays, and well, I see Andre has his hand raised, but I don't think I can have you speak because you are an attendee and not a participant. Oh, there you are, Andre. Yeah, there we go. Yeah, yeah.
Sounds like yes. Okay, yes. If I understand correctly from Raul,
Mhm.
I will be talking next week, Tuesday and Thursday at the same time as Andrew talked this week. And as
Okay.
Andrew has said, indeed, I will use this NP scattering data as one of the main examples just to tie it to the lectures we've been doing, but I'll also introduce a couple other random, simpler examples to begin with. And
Right.
for those of you who have been listening, if you feel you if you're struggling to follow Andrew's discussion because it's more technical than your current.
Andre, you stopped talking.
I'm back.
Yeah.
Okay, no, I got converted to a panelist and then I got muted. Okay. See if my setup works. There we go. Okay, hello everybody.
Okay.
So I was just gonna say, I will try to wrap the entire discussion of the data analysis such that you don't need to know any of the physics at all. It's just going to simply be using these physics examples Andrew had as a motivation to say, here's some data, here's a fit function, let's try to understand how to analyze it. So please don't worry about understanding the underlying physics. We can ignore that. This wasn't to suggest that Andrew is too technical either, just in case somebody was feeling that it was above their head. Don't feel like you have to understand it to understand the data analysis.
Yeah. And while they're, I think another way of saying it is like, I think you're building off me conceptually, but not in technical ways. So, yeah. And it's a lot to cram in 2 lectures of what my entire field is. But I hope to at least give you a flavor of what we do. And if you find it interesting, then, we can chat more about it. All right. I think Raul has stepped away, so maybe I'll just call the shots then and just wrap us up. So yeah, so thank you very much. And I'm available on Slack if there's questions. I'll try to answer them when I can. And I'll put these slides up as soon as I eat lunch.
Thank you, Andrew.
Thank you.
Now that I have
Thank
analyst
you.
control, no, I still don't have reactions. Give you the virtual applause.
Well, thank you. Yeah, I'll virtually accept it. All right. Well, thank you, everyone.